بسم الله الرحمن الرحيم والصلاة والسلام على سيد المرسلين وعلى آله وصحبه أجمعين. Distinguished speakers, dear colleagues, welcome to our workshop, Progress in Brine Mining and Lithium Harvesting. First of all, let me thank the organizing committee, Dr. Ismail Abdelaziz, Dr. Mohammed Yassin, and KAPEX, represented by Dr. Mohammed Al-Muhani for their technical support. And I would like to take this opportunity to introduce our small family in the center. We have 12 research scientists in the center: Dr. Asif, Dr. Ismail, Dr. Nadim, Dr. Jilani, Dr. Bilal, Dr. Mohammed bin Afi, Dr. Bahiro, Dr. Amir, Dr. Abdul Wahid, Dr. Mohammed Yassin, Dr. Sani. They come from different disciplines: chemical engineering, mechanical engineering, chemistry, geology, and we all together work in harmony to serve this center. Our mission is to pursue solutions for local and global challenges, and we are committed to education, in which we are involved in undergraduate research, UXplore program, and other programs in the university. The target sectors for our center is oil and gas, mining, wastewater treatment, desalination, energy, and environment. We receive sustainable fund from KFUPM, and we also have client-funded projects. In addition to the full-time research scientists in the center, other faculty members are also involved in the research activities of the center from different departments in the university: chemical engineering, chemistry, civil engineering, petroleum, environmental science, mechanical engineering, mathematics, biology, and physics. We are trying to tackle some of the grand challenges, such as the groundwater depletion, fouling resistance, resistant membrane, organic solvent membranes, produced water, brine mining, and gas separation. Those can be classified into themes, in which we classified it into 4 themes that we are currently working on: water security, water treatment, desalination, and membranes. We have different available technologies in the center, starting from reverse osmosis, membrane distillation, forward osmosis, capacitive deionization, electrodialysis, and gas separation. And we are currently working on developing other technologies, such as the membrane bioreactors and fuel cells. During the past year, we conducted different workshops on water security, on reverse osmosis, on water security and climate change, and on produced water. And now we are here to listen to our speakers on an important topic: brine mining and lithium harvesting. We invited distinguished speakers from SWIC, Saline Water Conversion Corporation, Dr. Chris and Dr. Vincent from University of Texas, and Dr. Gioli from Calabria University. Our topic is brine mining, which is the extraction of any desirable compounds or elements from salt solutions, such as brackish groundwater, seawater, and surface water. Brine mining operations may extract numerous materials from the same deposit, and production may include lithium, as well as a variety of other elemental substances and compounds. The actual process for recovering lithium from brine varies depending upon the source of the brine, whether it is continental, geothermal, or oil field deposit. However, there are alternative sources of lithium though generally in such a small concentration that commercial extraction simply isn't viable. With the rising demand for lithium, however, some facilities are implementing new technologies that are inspired by standard brine mining techniques, but are instead designed for use with produced water, for example, and brine waste streams, such as the hydraulic fracturing brine. To make more efficient use of resources, some companies are incorporating water and wastewater treatment technologies to recover these dissolved metals and salts from the fracking brine, as is the case for lithium recovery operation at the shale gas fields in Texas. But there are relatively few known lithium deposits across the world, prompting concerns about scarcity as existing lithium mines are depleted. With seawater as abundant as it is, researchers and metal producers alike have begun to take a hard look at oceans as a potential source for lithium. So it is possible to extract lithium from seawater. That's what we are going to hear from our speakers, or better yet, to combine the process with desalination plants. Is it feasible for Saudi Arabia? Is the process green process or harmful to the environment? And what are the challenges? Is Saline Convergent Corporation interested in such activities? These questions are left for our speakers to answer. For now, let me introduce my friend, Dr. Turki Baroud, who will introduce the speakers. He's an assistant professor and the chairman of the Material Science and Engineering Department with a PhD degree in mechanical engineering from Cornell University. Dr. Turki.
Okay, thank you so much, Dr. Isam, and I'd like to greet everyone. Hello and ni hao and hola, and konnichiwa, good afternoon, good morning, and good afternoon, good evening, wherever you are. So I would like to remind you again, this forum is coming to you from King Fahd University of Petroleum and Minerals. My name is Turki Baroud. I'm the chairman of Material Science and Engineering Department, and also I'm an affiliate of the Water Security and Membrane Center. So as Dr. Isam gave a background about today's forum, so the production of several metals and chemicals has become increasingly critical for sustainable development. Lithium and other metals and chemicals and valuable commodity moving forward as we see the push for clean, sustainable energy today. So mining remains an essential and growing part of modern industry, but also brine mining also is gaining more attention. And today we're trying to hear from renowned speakers to talk about the challenges, opportunity and challenges with the brine mining. Now, let me introduce our first speaker for today, Dr. Christopher Fellows, who is the Senior Anti-Scaling expert at the Saline Water Conversion Corporation, Saudi Arabia. Also, he's the Adjunct Associate Professor at the University of New England, Australia. Dr. Fellows received his PhD in physical chemistry in 1999. And before coming to Saudi Arabia, he worked at the University of Sydney and the University of New England in Australia. His research are in the scale control, polymerization mechanisms, very broad topic of fundamental thermodynamics and kinetics of chemical processes of relevant industry. And now in the SWEC or SCWCC, one of the topics that he's very interested in is the modeling of processes for extracting valuable component from desalination brine, which is brine mine. Dr. Fellows authored over 100 papers, and also he's a member of the IUPAC Polymer Division and the chair of the IUPAC Subcommittee on Polymer Education. Dr. Christopher, it's really a pleasure to have you with us today, and the floor is yours.
Thank you very much, Dr. Turki. It's a great pleasure for me to be here as well. Thank you for that wonderful introduction. And thank you also to Dr. Isam for the very good overall introduction to the program. In a way, you said most of what I'm going to say, so I will be fleshing out your remarks in more detail as we go forward. So I work at the Desalination Innovation Technologies Research Institute, which is the research arm of the Saline Water Conversion Corporation, which I'm sure you all know. And I'll be talking today, giving a broad overview of the big picture with lithium, and then taking you through some techno-economic analysis that's been done primarily by my colleagues, Dr. Im and Dr. Lee at the DTRI. So we all know that lithium is one of the critical materials for the future. So this was, when I was younger, I only ever saw these little tiny lithium batteries, but now we're getting larger lithium batteries up to car-sized lithium batteries, which obviously requires a much greater amount of this material. And lithium is unique, of course, because it is the lightest metal possible. So when you're looking at any electrical process, you've got the biggest bang in terms of electrons per amount of mass that you have to move around. So with the increasing amount of electric cars out there, the increasing number of mobile phones and laptop computers, there's a growing need for lithium. And the last year has been particularly interesting for lithium and has generated a lot of attraction. Lots of people have sort of come out and opened their eyes wide to see this extraordinary sort of price spike in lithium that doesn't really seem to have abated yet. So we have approximately a 8-fold increase in price over about a year. So prices of lithium are measured in terms of tons of lithium carbonate equivalent, typically. So lithium may be used in various salts, but lithium carbonate is the main form in which it's initially obtained. So here's a graph over a longer time period that shows you the growth in lithium production, of course paralleling the growth in consumption over that time. And the events of the last few years, you can see a dip in production with a increasing demand translating into those very high prices. So of course it would be foolish to make decisions based on the prices over the last year. It makes more sense to look at the long-term trends. Now I'm going to take you through two of my favorite quotes. So ever since people first analyzed seawater and figured out the bewildering, the amazing variety of things that were in it, people have been dreaming about getting those things out, extracting that value. So this gentleman said, 10 years ago, commercial extraction of any of the elements present in the ocean was as impossible as alchemy. Today it is unaccomplished fact in the production of bromine. And I feel safe in predicting that within the next decade, we will be able to recover gold, silver, radium, and all the other untold wealth from the sea. Now that we have made one dream a reality, it is only a matter of further technical development and refinement of process before we make the sea loosen its hold on a fortune so fabulous that it staggers the imagination. So this appeared in Popular Mechanics magazine in June 1934. And this gentleman was Thomas Medgley, the vice president of the Dow Chemical Corporation. So yeah, a very powerful man with a big vision, which has not yet come to pass. It's true that it's just a matter of further technical development and refinement of process, but it's quite a lot of technical development and refinement of process to bring this vision to reality. So now for the next quote, this is another one of my favorite quotes, and this applies to just about everything. I often say that when you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot measure it, you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the stage of science, whatever the matter may be. So it's always important to think about things quantitatively. So I'm going to take you through a few slides about seawater and what's in it. So quite a few review papers show graphs like this. This is one of our own that was just accepted recently. So on the x-axis, we have the concentration in parts per million of various elements in seawater. And on the y-axis, we have the price of these elements. And various people have put out various graphs like this with various lines, and we've put some of the lines that have appeared on other people's graphs on our graph here. But you can see in every case, we've got two zones. We have a zone on the left where the concentration is too low or the price is too low for that to be a viable commodity to get from seawater. And then we have a region on the right where we have things that it is plausible to extract from seawater. And you'll see on our version of the graph here, the lithium carbonate is sitting right in the middle there. Pretty much dead center right above the one. So one of those tricky cases. Now, a more dramatic way to express this visually is to multiply the two axes together. And note that this is a log scale here. So I'm going to take you through the main commodities that we can get from seawater as the product of the price and the amount that's there. So another commodity that had a big price spike last year was actually oxygen. You might have heard about this surge in medical oxygen supplies, especially in India. So quite tragic situation there. And if we were to convert 1,000 meters cubed of seawater to its components, its elemental components, the most valuable one by far would be oxygen. But of course, there are other sources for oxygen that are probably more convenient than electrolysis of seawater. Whenever we're talking about the amounts of what we can get, as well as these numbers, which are just the numbers that would sort of fall out magically if we got these things, we have to consider what are the alternative sources and what is the cost involved in getting these things from seawater compared to those alternative sources. So seawater being so salty isn't a particularly good source of hydrogen as well either. Hydrogen being another commodity that has a lot of buzz around it. So I'll just get rid of oxygen and hydrogen and show the things that are slower down on the graph. So here are commodities that you can get without adding any extra elements. You might have to do some chemistry on this graph, but we're not adding anything else to the seawater. And you can see on the left-hand side, we have caustic soda and hydrochloric acid, the products of the chlor-alkali industry, and metallic magnesium. So if we got everything in these forms out of seawater, those would be our three most valuable products. And you can see we still can't see lithium carbonate appearing on the x-axis, on the y-axis, enough to distinguish it from the baseline. So I'm going to cut out a few more things, cut out the things that you need to do significant chemistry to get to, and just show things that in the form that they appear after you do the first extraction from seawater. So these are the things that our focus is on at the Saline Water Conversion Corporation at the moment. We're looking at extracting sodium chloride for the large chlor-alkali industry that we have in Sharqiya, looking at extracting bromine and trying to find markets for these magnesium salts. Ideally, there'll be a producer of metallic magnesium that will want to add value to these magnesium salts. So we can just see lithium appearing on the axis. So when we look at this analysis, it looks like lithium is quite a small commodity. Even with those high prices, the concentrations in seawater are just so low. And yet there's been a lot of research interest, some very exciting, very interesting science, interesting chemistry been published very recently, interesting physics, proposals for producing lithium from seawater. And these are publications in high impact papers that have acquired traction from industry, people who are interested in these papers, even though the concentration of lithium is so low. So I'm going to get back to these papers, and particularly one where they did do a preliminary techno-economic analysis and came to the conclusion that it would be viable to produce lithium from seawater. But first, I'll take you through where lithium comes from today. So there are multiple sources of lithium around the world. There's what's called the lithium triangle, of Argentina, Bolivia, and Chile. And here there are a number of salars, so basically dry salt lakes underneath which are brines rich in lithium. And notably, these are rich in lithium and relatively low in magnesium. Then there are what I might call unconventional brines. There are many sources of these around the world, associated with geothermal activity, associated with oil fields, associated with other lakes which have a much higher magnesium to lithium ratio and are found typically in other inland highland areas around the world. There are also lithium-containing clays, lithium-containing earths, and lithium-containing hard rock deposits. So starting with the mineral deposits, there are several hard rock ores of lithium that have concentrations between 0.5% and 3% in the solid of lithium, things like lithium aluminium silicates, lithium sodium phosphates, and these other ores, which are in forms of mica, it's like flat sheets, that's lepidolite, clays, and then this soft mineral, jaderite. And the largest deposit that's worked in the world today is the Greenbushes mine in Western Australia. You can see the mine there. That's its whole footprint, still looking quite pleasant and nice a little ways away from it. It produces 160,000 tons per annum lithium carbonate equivalent, and the reserves are estimated at greater than 4 million tons of lithium carbonate equivalent, and those reserves are reserves with a concentration of 2.8% lithium. So there may be greater reserves with a lower concentration of lithium. So this is basically the cheapest lithium in the world. Lithium concentrate from Western Australia is exported for processing to all over the globe. This is a deposit that's coming online from that mica-based mineral, lepidolite, in Namibia, in Southern Africa. The project proposal here is to mine the lithium and ship the concentrate to the Emirates for processing. So we have a local source of lithium that will be reliant on the relatively cheap energy we have in this region. Projected to produce 7,000 tons per annum from reserves of 120,000 tons per annum. Much lower concentration, but still significant. In Mexico, there are huge reserves of a lithium-containing clay that have been identified in the state of Sonora. It's estimated there are more than 8 million tons of lithium carbonate equivalent at about 1% lithium concentration. In Serbia, Rio Tinto had a project for producing 58,000 tons per annum of lithium from this soft mineral jaderite, greater than 2 million tons of reserves. They've had to cancel that project because it's a very green and pleasant country, and the locals don't want it dug up, so the government has stopped that mine. So there are significant mineral deposits with concentrations of lithium in the rock of 0.5% or greater. And then there's this wide variety of brines, brines beneath salt flats, brines in salt lakes, geothermal brines, and oil field brines. So looking at the concentrations here, you can see that there are at least 2 orders of magnitude and up to pushing 4 orders of magnitude, the sort of concentrations that we have measured in desalination brines. And we know our desalination brine concentrations are correct because the concentration of lithium in the ocean is very well known, and the concentration factor going to our desalination brines is very well known. There's no way to magically create lithium and concentrate it in the brine. So among these lithium sources, the largest is from that so-called lithium triangle. Chile has awarded 5 additional 50,000 ton per annum lithium carbonate mining concessions. The reserves are estimated as greater than 9 million tons there. The Smackover formation, this is in Arkansas, in the southeastern United States, a very significant oil and gas formation, which is also an important source of the world's bromine. The lithium concentrations there in the hundreds parts per million. They're beginning to process that now, looking at producing 20,000 tons per annum, and the reserves, at 20,000 tons per annum, that will last for well over 100 years. So given this great richness of hard rock deposits, soft rock deposits, brine deposits of various kinds, what is the rationale for technologies that extract lithium from seawater? The real rationale for these technologies, we believe in DTRI, is for treating brines that have similar chemical composition to seawater, but are much more concentrated. So the problem with high magnesium concentrations is that the reagent that you add to precipitate out lithium carbonate, typically sodium carbonate, you can see here, also reacts with magnesium. So if you have a magnesium-rich brine, you end up with two problems. You're using a lot more reagent to precipitate out the lithium that you want, and you're ending up with a mixture of magnesium hydroxide and lithium carbonate, which you have additional effort to separate. So this is why Bolivia, which has sometimes been described as the Saudi Arabia of lithium, is not actually yet the Saudi Arabia of lithium, because the Salar de Uyuni, which has the vast reserves of lithium, also has a high magnesium to lithium ratio. So it's more expensive to extract lithium from that formation than it is from these other formations in Argentina and Chile. So you can see that standard seawater, we have two problems. We have a low concentration and a very high magnesium to lithium ratio. But any technologies, such as all of these technologies described in these recent papers, and the technology we'll hopefully hear more about later this evening, are good for extracting lithium in the presence of magnesium. And this opens up all these sort of formations in the brown here to be more effectively exploited for lithium. So I don't want to overrun my time here. I'll take you through now the analysis that we've done of the process published recently by Professor Lee and his group from the kingdom here, the King Abdullah University of Science and Technology. So they estimated in their paper an energy cost of about 75 kilowatts per hour per kilogram of lithium. So this is basically the energy cost of the electrolytic process. This does not include the other costs involved in producing lithium. So the analysis we've done is we've had a look at some other studies that have tried to estimate the overall OPEX and CAPEX of lithium producers under different environments, and taking those other components of the cost and added this electrolytic cost and tried to adjust exactly where the cost of producing lithium from seawater would fall in comparison with everything else. So this is from a publication by Johnston and Hall in 2019. So this is the proportion of the OPEX of different lithium carbonate production from brine projects around the world. All cost there of 180 to 400 per US dollars per ton is from normalizing them all to 558 parts per million of feed brine. So you can see that the primary cost here is in the reagents, the cost of that sodium carbonate for precipitating out the lithium. And then we have these other costs. The salt harvesting comes from the fact that the brine comes out less concentrated than it is ideally for this treatment. So it has to be concentrated by the sun. The salt, sodium chloride crashes out, and then we have the more concentrated bittern left over for the chemical treatment. So we can get rid of the salt harvesting component if we're going to be treating a brine electrolytically, and we now have to add the additional costs for preparing this concentrated brine by a process similar to that of Professor Lee and his group. So if we just take that electrolytic cost, that turns out to be about 900 US dollars per ton of lithium carbonate at the industrial cost of power here in the kingdom. But there's this additional very significant energy requirement that we need to incorporate, and this is the cost of moving the very large amounts of water about in order to extract this amount of lithium carbonate. So with 0.18 parts per million of lithium, so this is the typical concentration in seawater, we have to move more than 6 million tons of seawater per ton of lithium. And in DTRI, because we deal with a lot of problems within SWEC, which involve moving large amounts of water and pumping them through membranes, we have a good idea of the energy cost of moving this very large amount of water. And so the energy cost of doing this through the process as described by Professor Lee et al. Dwarfs the energy cost of the electrolytic process. So we get an approximate cost of greater than $5,000 US dollars per ton for producing lithium by this process. So that's the OPEX. On the CAPEX side, for brine projects, most of it is these evaporation ponds. We can get rid of those. But the plant that we need is going to be considerably more complicated. So I've taken a rough estimate here of getting rid of the brine extraction wells, getting rid of the evaporation ponds, and doubling the cost of the plant. So this gives us, if we amortize it over 25 years, cost of about 800 to 2,000 US dollars per ton, depending on whether we use the Argentinian or the US typical CAPEX values. So our overall cost of producing lithium for this process, you can see is way up on the right-hand end of these reported costs of production from various sources. So obviously someone is doing these processes in the orange here. Someone thinks, sorry, in the dark green here. Someone thinks it's worthwhile to do that, but we're getting it from seawater is right over at the most expensive end of lithium producers. So in the paper of Professor Lee and all, they suggest that the process will become economic by selling some of the byproducts. Their process of the electrolysis, there's hydrogen and chlorine produced as well, so we can take those into account. So if we have a process producing a certain amount of lithium carbonate, 20,000 tons per annum, we'd also need some buyers for a considerably larger amount of chlorine and a small amount of hydrogen. So any facility like this would be ideally placed in an environment like Yanbu Industrial City or Jubail Industrial City, where we have large chemical industries nearby that are a market for chlorine and hydrogen. So I've gotten to this point in my presentation, been talking for quite a long time now, and I haven't mentioned desalination hardly at all. I mentioned brines briefly once, but desalination brines briefly once before. How does the potential extraction of lithium fit into our SWEC vision for production of valuable components from brine? So we see a facility that's just producing one thing as not being particularly viable. What we're looking at is ideally an integrated facility where production of different materials would support one another, where we would have identified buyers for all of the most significant products coming out of the brine. And once the sodium chloride is removed, you end up with a concentrated bitter, and we can remove potassium chloride from that, which has value as a fertilizer. We can remove bromine from that, which, as you know, is critical for clear brine fluids in the oil industry. And what's left is a concentrated purge, which has a very much higher lithium concentration. So we can do similar analysis to what I've just presented for seawater, for desalination brine, and for the purge that's produced from our integrated brine mining facility. And if you recall what that graph with the different slices looked like, we're sort of moving back towards the center. Maybe if we're extracting lithium from this purge, which has the low magnesium and the high lithium, maybe that's reasonable. It's looking pretty good. But there's something else missing from this analysis, and that's the amount of material that's available to extract lithium from. So from our integrated plant, the amount of seawater that we can feasibly treat is limited by the markets of the other commodities. And that's going to be very much less than the total amount of brine produced by the Saline Water Conversion Corporation. So I'm just going to put in one other sort of brine. I'm going to replace the desalination brine with oilfield produce brine. So look at those numbers. They've come down significantly because the concentration of lithium is significantly higher. So I've been trying to look around and find some good values in the literature for what concentrations of lithium we do have in oilfield brines in this region. So not very far away. Their average values for two of the large oil fields in Kuwait, 1.1 and 1.9. So that's 5 to 10 times what we have in seawater. Other references also for Kuwaiti brines are looking even better there. Those quoted 4.5. Highest value quoted in this Al-Farhan and Duane paper is 6.6, so significantly better. Very recent paper reports on a brine from the kingdom. Haven't been able to identify exactly where it came from, or if there just seems to be some methodological uncertainties in this paper, but suggesting up to 70 parts per million, which is certainly getting up there as a competitive concentration for brine. So if we compare like with like and look at the amount of lithium carbonate that could come from different sources, we're projecting at SWEC a plant that could produce 2 million tons per annum of sodium chloride, which is a large amount of sodium chloride. I think that's about pushing 10% of the kingdom's total consumption of sodium chloride at the moment. The cost of this plant is approximately $400 million US dollars, and this would produce as a byproduct approximately 20 tons per annum of lithium carbonate. If somehow we were to take all the SWEC brine and do the same process to it, we'd have a gigantic lump of salt on the world markets, gigantic capital investment, and we would be producing, or I should put a 2 in there, sorry, 2,000 tons per annum lithium carbonate, which is very small compared to the production of any of these projects I've been talking to you about, any of these unconventional brine or hard rock mining projects. So I guess what I've come to say to you tonight, what my take-home message is, that desalination brine is not a good source of lithium. It will take, I don't know, some dramatic, bizarre changes in the world for us to ever make money extracting lithium from desalination brine. So there is hope for the kingdom, though. All of these wonderful technologies that make it more viable to extract lithium from desalination brine also make it more viable to extract lithium from other high magnesium, low lithium brines. And it is certain that there are significant resources in the kingdom of these other brines. So we don't know much about these oil field brines. We don't know much about the subsurface brines in the Rub al Khali. I know there are natural brines there. I found one paper that quotes a significantly higher lithium to sodium ratio. So there may well be natural brines there that are viable for this process. So if we want to achieve lithium self-sufficiency, which is a laudable goal, I think we should be investigating these other potential lithium-rich underground brines in the kingdom. And that's all I have for you this evening. Thank you very much.
Thank you, Dr. Christopher. That was very informative. Thank you so much. So let's leave the floor for our audience. If you'd like to ask questions, I'd like to remind you that you can write a question in the chat box, or can also raise your hand if you'd like to ask questions using the mic. Okay, so until we receive a question, let me ask you a question, Dr. Christopher. Yes, it might not be economically viable to extract lithium from brine, but considering the traditional mining, considering the impact, the environmental impact that come with it, right? Air pollution, water pollution, soil erosion, can the brine mining can be viewed as being more environmentally friendly and can be a way to extract lithium, although economically is not that interesting.
Yes, I have heard that take before. So that is the best argument to me for producing lithium from these sources. So I know that the European C4 value process, the people involved in producing lithium there see this as their angle, a way to produce green lithium. However, I guess my take would be that these oil field produce waters that are coming out that need to be treated anyways, that are a waste in themselves, the producing lithium from them, I don't see how that would add to the environmental impact. I mean, it's part of mitigating the environmental impact. So that could also be sold, I guess, as a green lithium. It's a byproduct of a process for removing a pollutant.
Right, good. So let's see if we have a question from the audience, or we can move to the next speaker. So someone is raising his hand. Dr. Isam, تفضل Dr. Isam.
Yes. So what is the concentration that will make the extraction of lithium from brine a feasible one for the desalination plants?
Okay, so it's I guess it's the product of the concentration and the amount of material coming through. I guess I don't see it as a matter just of concentration of it ever really being viable. So with the if there's a lithium source, I would say of 5 parts per million or better, it looks like that could be treated by these new methods and be competitive with the conventional brines. That's my feeling, which might be a little bit ambitious. So we can produce that concentration in desalination, but then we're only producing a very small amount of that.
Yeah. So don't you think that the cost is highly dependent on the method used for extraction of lithium? And for example, the conventional brine evaporation bonds and all of that, is it comparable, for example, to electrodialysis? Does it make any difference in the cost at the end?
I think the conventional method is still very much cheaper than electrodialysis. So in terms of desalination, there's only a few plants in the Far East that use electrodialysis. It's just not competitive with the membrane-based technologies, and I don't see it really in being competitive with solar evaporation, where you're getting your energy basically for free. So we've looked into electrodialysis in SWEC for other mineral harvesting applications, not lithium. So looking at ones that are present in much higher concentrations, and even there it seems to be uncompetitive. Not that further research might make it more competitive, but at the moment it doesn't look like electrodialysis is going to be competitive.
Okay, thank you.
Okay, great, thank you. So I think for the audience, if you still have questions, you can just add in the Q&A. We can answer it toward the end of today's program. Now, I would like to thank you again, Dr. Christopher, for your time and for this presentation. I don't want to stop you because I was very interested to hear your views and really appreciate sharing your opinions. But I think we have to end the event for today. It looks like different opinions, but I think all of us agree at the end of the day, the supply chain of minerals is very important. We have to secure materials to feed different technology. Here in the kingdom, in Saudi Arabia, we believe in that. Today, the kingdom is looking at the mining industry to be, the third pillar for the economy. Looking at more than 700,000 square kilometer in the Arabian Shield, full of minerals, where the kingdom is looking at itself to be center of mining, where it might be, and hopefully competing with other countries that we mentioned many times, Professor Drioli, like China. By the way, most of the European investors, when they came to the mineral forum that took place 3 weeks ago in Riyadh, I think most of them, they were very excited about the movement that we see here in the kingdom when it comes to mining, whether it's in the traditional mining or also the brine mining. Good news they heard from this week. I don't want to keep this going, although it was very informative session. I would like to turn the mic to Dr. Isam, the director of the Water Security and Membrane Center, to deliver his closing remark.
Well, thank you, Dr. Turki. Finally, I would like to thank the panelists for their time and excellent presentations. Dr. Chris talked about mining in SWIC, and it is very important to Saudi Arabia. We learned that maybe now we should not concentrate on lithium. Maybe we should focus on other minerals. There are more work to be done in this regard. Dr. Venkat explained the transport mechanisms and membranes, and how to engineer the membranes to be highly selective and to take inspiration from the highly selective materials in nature. And finally, Dr. Drioli talked about the integrated desalination and mineral energy. He reiterated his words that I heard from him a year ago. Eventually, we will get free water from the desalination company. And the takeaway from him today is, don't worry about the economy until you find a solution. That's very inspiring, Dr. Drioli. And we appreciate your time with us, Dr. Chris, Dr. Drioli, and we hope to see you later. And thank you all for staying with us late tonight. And I wish you a fruitful research journey in these enlightening speeches. Thank you all. And we hope to see you soon, inshallah. Thank you.
Yep.